Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about EV drive motors or traction motor. So let's dive deep into it. Now you have to understand the world is moving towards it, be it two-wheeler, be it three-wheeler, be it car, be it tank. And yes, I included tank, including airplanes also. So world is reaching a point where they do need EV traction motor, even if in sometimes it's just being driven by basically diesel generator like a diesel locomotive. So everybody needs good traction motor. So what are the requirements here? Well, any motor that is used for propulsion is classified as traction motor. So even though my ICE engine has a lot of electrical pump that uses for wiper fluids and things of that nature, those are not classified as traction motor. So that you could literally find a company that is like great at like making millions of motor, but they are really horrible at making traction motor. And there is this other company only makes traction motor, because again, this is a completely different classification. So how do we classify it? We classify it with the tag traction motor. Now you will hear two puppies spat out very commonly. First is high speed. Now what the hell that means, high speed? How do you know what is high speed? Well, it does not mean what is the RPM. It simply means for intended application, you have to reduce the RPM to increase the torque. Meaning, let's just say your wheel is supposed to rotate at 1000 RPM, but your motor rotates at 1000 RPM. Motor rotates at 10,000 RPM. It will be classified as high speed motor, because to utilize the motor, you have to step it down. You have to have a gearbox that slows it down. So benefit of slowing it down, your RPM goes down, benefit torque multiplies. So high speed motor generally implies that it does not have the torque to direct drive. So if you are doing direct drive, for example, a two-wheeler, it could literally have a motor that is directly doing, that will be classified as high torque motor, not high speed motor. Now let's say some other EV where they have a motor then going through belt drive, those will be classified as high speed, because they are inherently trying to amplify the torque, because again while the RPM is there, torque is not there. So high speed simply means that you have to step it down to get the oomph needed, and high torque simply means you can direct drive for the application. Now application could be anything. Basically, if you have electric motor that are used for a plane parking, so to say, those puppies are idiotically torquey. So for those sort of scenario, like, bro, I don't need RPM, I need torque to move the planet. So those will be high torque motor. Now, so far, everything about this is not that difficult. We have industrial motor. They have been running, and you could literally find motors that are 1 century old and still goddamn running. So what's the issue here? Well, issue is most of the things that can run that long generally go through maintenance cycle. So even if I talk about like AC mains motor that we utilize for water pump, if it's a big building, lot of people depend on it, they will have periodic services. You can't do servicing in electric traction motor. Even train motor you can do traction servicing, but when it comes to electric traction motor, it's put and forget. Heck, even motors that are going into basically electric truck, they are also much more hard, getting harder life compared to truck engine itself. Engine supposed to be rebuilt after 100,000 miles or something like that. So for that reason, you have to understand, it's put and forget. Every aspect, every nut and bolt, every oil, every bearing surface, all of those has to be put and forget, meaning everything else should fail in your vehicle before the motor fails. So meaning you could have a scenario where battery poofs out, most likely you throw away the car, that's a different thing. Your inverter fries out, again that's why generally inverter are built such a way that you can swap it, because again electrical things could happen, oops happen, but it should never be a scenario where it's like, oh, motor fried itself. So no, that's not acceptable. You have to design everything so that does not happen. Downtime is not acceptable, and maintenance is also not afforded. So you have to design everything around that. Another aspect is there is one motor topology that gives you best of everything. It's like, I have the low RPM torque, I have the high RPM efficiency, I got everything under the sun. It's just that I am very difficult to manufacture. So manufacturing matters. Can you actually stamp these puppies fast enough to actually justify the load? It's one thing to design one bespoke motor every few months for, let's say, electric aircraft. Those are very bespoke, that's one thing. But when you're talking about like a car that could be mass produced, as in like few thousand pieces per day, yeah, at that point in time, that matters. So manufacturability also matters. It becomes another lever that has to be pulled or managed. And stable supply chain, because when we were in that bespoke era of the early 2000s and 2010 electric vehicles, people were putting magnets in it like there is no tomorrow, because again there was demand was so little and supply was like saturated, so to say. So it's like, who cares? Now everybody wanted it, then randomly people realized, hey, only few countries have supply of this, and price went lol. So supply chain also matters. And what the heck you're gonna do at the end of life? So end of life, we have not reached that maturity yet, but it's same as smartphone. Early days nobody cared about about what the heck is going to happen to smartphone afterwards, but now people do. Same thing will happen with motor also. So this is the need of the hour, so to say. So now let's introduce the Thanos of it. So which is electricity. Now electricity, whenever you're talking about these sort of thing, you generally get 3 vector control and you have to Thanos it, perfectly balance it. Vector number 1, voltage. So what about, what if I increase the volt to get more power? You can do it, but what is the limiting factor? Limiting factor is insulation breakdown. You are talking about copper conductors. These have insulation around. How thick is that insulation? How highly rated is that insulation? Can we have rotors or stators that could support 11 kV? Of course, that's how your power plant generator works. Problem is, those have thick insulation on conductors. Thick. I mean like double C kind of thick. So they're thick. Can you afford that to put that in your motor? If yes, go YOLO in voltage. If not, come down to earth. So that's the limiting factor. So you're like, you can literally watch the early days, battery voltage were like 200 volts to 1998, then it went to 400 volts. Now Kia is like 800 volts. Some bus companies 1500 volts. It's like, why can't just go to 5000 volt? It's just like, you can do that. It's just that insulation is like, bruh, chill. So voltage is limited by insulation. If tomorrow some new quantum technology is in time where it's like ultra shield, which we can have micron thick and like we can handle 10 kV, every motor will start running on 10 kV. So insulation is the limiting factor of the voltage. So you have to balance that. Then it's like, okay, let's say I peak the voltage as high as I can get. That's the limiting factor. What else I can do? You can increase the amp to get more oomph out of it. So amp is limited by conductors, aka resistance, aka thermal runaway. Meaning conductors in India are trolled because somehow Indian government rates it at 25 degrees Celsius. I'm like, we live in India. Rate it at 50 degrees Celsius. So you have a conductor, and conductor you are dumping current into it. Cool, awesome. Now conductor heats up because again it's not a perfect conductor, it's not superconductor, so it's gonna heat up a little bit. Then you pump more, it heats up even more. Now here's the deal: the temperature rises, the resistance also rises. Benefit of that or penalty of that is once that happens, it's much more heat generation. So every increase of amp, you reach a point where it's like it's literally just melting itself. Thermal runaway happens. You dumped more amp, it got hotter, that increased the resistance, increased the waste heat. Now it created this feedback loop and voila, it melts away. So amp is limited by thermal runaway. As long as you can cool it or ideally use superconductors, you will be limited by that. So amps is also limited. Okay, so you can't increase voltage like YOLO, you can't increase the amp like YOLO. What can you do? Well, the third vector opens up, that is frequency. Whenever you're talking, and frequency also applies on DC, especially on BLDC motor, it still has operational frequency. Like you can see how it's going tuk 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 tuk. You can see it. What is the switching frequency? And in AC, frequency. Now frequency, you will be like, what if I increase the frequency? Does that work? Absolutely. That's how we went from like a ginormous motor that barely had few horsepower that we use for water pumping, because again they are running on 50 hertz, same characteristics, same voltage, same amps, but then we just turbocharged the frequency. We went to aircraft companies like, bro, pass down the technology of 400 hertz. And now every motors are like 400 hertz. Or what if you're like, okay, if more hertz equal more good, why not increase it even further? You can. It's just that there is another penalty known as skin effect. You will reach a point where even though you can have giant thick conductor, and conductor is like, no bro, I'm not this thick, I'm this thin. It's like, why? Only skin is utilized, the core is wasted because of the high switching frequency. So skin effect is the upper limit there. So that's why all three are limited by each other. So you have to be like, what if I increase the amp? It will melt. What if I increase the frequency? It will not use itself. Basically the conductor will be wasted. What if I increase the voltage? Insulation will break down. So whenever an engineer gets down to design a traction motor, these are the three levers they have to balance like Thanos in order to give you. And then you have fourth vector, that is design vector, which is we call pole count. It's like, what if I want speed? You put poles. The more poles you, basically less pole you put, higher speed you get. The lowest you can go is 2 pole. That would be the highest RPM motor you can get, given the frequency is same. Now you're like, okay, that gives me high RPM, but I do not want to spend on magic bearings. I'm not even joking, Tesla bearings are that. It's not even classified for that RPM. They're like, okay, what if I squirt oil into it continuously to keep the RPM manageable? Because bearings are like, bro, I do not certify the bearings above 20,000 RPM. It's like, if you want to run it remove the seals, squirt oil directly onto it and hope for the best. So if you do not want that, it's like, what can you do? Well, you can increase the pole count. Now, what are the benefit of that? Well, reduction of pole count gives you speed. Increase of poles gives you torque. So like, what if I want to just torque the hell out of it? What if I want to put motor in the wheel itself and direct drive that puppy? Yeah, you're gonna have a lot of poles. So, okay, why not directly have a lot of poles and reduce the gear train weight and all that? Yeah, higher pole equals higher copper losses. They have to balance this also. Voltage, same thing. Now, voltage in older days directly translated to speed when you are talking about DC motor does not have the same thing with AC. AC is a bit more complex relation, but still has that thing. And in terms of efficiency, higher voltage is generally preferred because you can reduce the current, generally. And current, again, generally it means more torque, but there is a problem. The higher the amp you use, the more heating losses you have to deal with, so you have to manage that also. Frequency, same thing. Higher frequency equals speed, lower frequency equal torque, and if you want to reach the sweet spot, you have to balance against all of this, otherwise you will get stuck with skin effect. So this is the electrical vector that torque engineers have to design around. Basically, they have to balance all these four things. So what are the options? Well, we have a lot of options. Electric industry right now, EV traction is 25 years old. So we are reaching a point where almost all topologies has been used. So let that be very clear. All topology will give something and take something away from you. You have to be very mindful when you are employing any of this, unless there is one other magic motor, but I'll talk about that. So let's start with the first puppy, induction motor. Now, induction motors are very efficient. Now, like, aren't our induction motor very inefficient? Yes. Why? Because they are low frequency. There is a sweet spot. Once you reach that and copper losses goes down, you can reach ludicrously high efficiency on induction motor. So we use that. Super easy to manufacture, super easy. And again, you can increase from a lot of power from going from aluminum rotor to copper rotor. You can increase the power. Everything is awesome about that. Except there is this one thing, that rotor, fundamentally, because there is a slip, it has to cut through the magnetic line rather than being locked to it. Rotor heats up. And this was the brilliant idea of Tesla engineers. They were like, hey, everybody has induction motor, everybody has VFD to drive this induction motor, so why can we get the more power compared to everybody else? They were like, hey, what's the limiting factor? Is the runaway of the rotor heats up. Let's say rotor is 50 degrees Celsius, it has X amount of power. Rotor heats up to 60 degrees Celsius, the power goes down, and it goes down drastically. So they utilized the through hole system to run coolant in the rotor itself. That was the genius idea they had. It's like, hey, what if the rotor was cooled? And that allowed them surprisingly high torque, surprisingly early on. And people are like, how the heck this electric motor feels so snappy? It's like, cool the rotor. So induction motor gives you a lot of benefit, but takes away certain penalties. And the biggest penalty is the rotor would be fundamentally inefficient, meaning you have to figure something out with this. You can have airflow going through it, you can have a through hole cooling to it, but you have to do something with this. So, and again, it's not synchronous, so fundamentally it will be less efficient compared to a synchronous motor system. So you win some, you lose some. Then we reach into, let's say, 2010 kind of era. In that era, people started to dumping magnet like there is no tomorrow. So magnet AC synchronous motor. So this became YOLO. Everybody was happy about this. It was synchronous, it was efficient, and it has very high torque at low RPM. So you can get that lounge performance rather than requiring on ginormous speed down and stupid bearings. So again, stupid bearing meanings you have to pay too much for the bearing. So everybody loved it. And again, then people are like, okay, what's the penalty? Yeah, once everybody started to do it, suppliers realized, everybody loves our neodymium magnet. What if we increase the price? Where else they gonna go? So overnight, I could literally watch every supplier going from nope. So nowadays, modern cars don't even come with AC synchronous motor. They're like, nope it, because again, the magnet is too expensive. And there is another penalty, because the magnet content is so high, at high RPM, it limits itself. So low RPM torque, everybody likes it. Low RPM efficiency, everybody loves it. The moment you're like, what if I want my car to go from like very low speed to very high speed without gearbox? You want your RPM to go from 0 to, let's say, 5,000 or 7,000. Yeah, the higher RPM, it has back EMF issue, because rotor has so much magnet, it's like going through, Vadayam, it's doing Vadayam magnetically to your stator. Stator starts to induce what we call back EMF. It has to deal with that. Now, you cannot turn off the magnet at high speed, so you're stuck. So fundamentally, that created an issue where back EMF became a hassle to deal with. So there are some penalties. Back EMF was a significant penalty, and basically, cost made sure that nobody actually did more research onto it. Then we come to the current love child of every motor engineer, magnet reluctance motor. Now, reluctance motors, I do not even know why it's called as motor, because it's almost like you are rotating something manually. You cannot just connect it to three-phase AC and tada, it will not work. You have to literally have a VFD that has a rotor position and you are rotating tuck, tuck, tuck. It's almost like a stepper motor. How stepper motor has teeth? Now imagine, instead of having magnet to create you that teeth, north pole, south pole, you have stamping sheet. Now that sheet has path, because again magnetic flux follows the same rule as electricity. It tries to find the path of least resistance. Magnetic flux also wants to do that. So if you know the rotor position, you can switch on and off your stator in such a way that it tries to spin to the nearest point. Now it does work very awesome, but it has a similar kind of thing where it's like really good at high RPM, not great at low RPM. And again, driver complexity is off the roof, like it's bonkersly complex. But it's cheap. It's just sheet stamps. Almost as cheap as induction motor, actually cheaper than induction motor. But again, you lose all the money savings in the driver. Driver is idiotically complex. So magnet, but again, electronics got cheaper more than the magnet. So people are like, yeah, let's just deal with the electronics. And it has low back EMF at high RPM, because again, reluctance work with that. Now, then why do we put magnet there? Well, we put magnet for low RPM torque. Basically, we are marrying two people, basically magnet motors and reluctance motor, and they are getting into bed together in rotor. They are spinning round and round. So in that in low RPM domain, magnet is like, I got you, fam. At high RPM domain, reluctance force is like, I got you, fam. So that's how the current love child is born. So if you split apart 90% of motor that is in the field, you will get that. Now there is another low cost option, that is BLDC. Now BLDC is generally used for low cost system. Why? Even though the rotor and stator is more or less same as every other design, it has super cheap driver. Why? Because if you put oscilloscope, let's say to point A to point B, you look at the waveform, it goes from 0 to 100 to 0. Now compare that to AC system, it goes from 0 to 100 to 0 to minus 100. That's the difference between AC traction and DC traction. So we prefer BLDC motor when we have to keep the cost down, and it does have good low RPM torques and all that. But again, magnet content is high, so people are like, yeah, let's just use it for small things. Like in Indian system, when we have tuk-tuk e-rickshaw, so to say, those use that. BLDC fan, those make sense. But you're not gonna use that for like 10,000 horsepower, hulululu. Yeah, that's not gonna work. So BLDC, good for low cost. So if you want to keep your cost low, low cost scooty, go YOLO. Then we have my personal favorite, my love child, which is AC brushless synchronous motor. I did not made it, but I want this thing to be most successful because this is best of everything. Meaning it's like, what if I want the efficiency of induction motor at high RPM? Because we do not have back EMF. Well, to have back EMF, you have to control the rotor, as in like how much electrical energy in the rotor is there to make the magnetic flux. You have electromagnet there. You are like, what if I tone it down? You basically, the band of useful torque goes up exponentially, efficiency goes up exponentially. So high RPM torque, high RPM efficiency, all of those are maintained. Okay, cool, awesome. But what about low RPM? Like that's more or less as induction motor. But what about low RPM? This is like, no problem, bro. Because you are directly pumping electricity into the rotor, you can increase the basically electromagnet's power and be like, more power at low RPM. So now you have low RPM, synchronous speed, and much higher efficiency, because you have the low RPM torque. So torque is 0 super torque, and 10,000 RPM super torque, 20,000 RPM super torque, 25,000 RPM super torque. Nobody designs it for that because bearing cost becomes stupid, but you can do it if you want to. And you get this flat curve, like ultra flat curve, because there is no back EMF and does not have the issue of slip. Induction motors have slip. They have to have slip in order to work. It is inefficient. This puppy is like synchronous, baby. No magnet, baby. So why don't we use it if that is so amazing? Well, we do. Every power plant literally runs on this. It's like, it's not a new thing. It's just that somebody figured out, hey, those things are made for generally 50 hertz or 60 hertz. What if we amplified it so we can shrink it down? Boom, you got it. And it does have penalty in terms of rotor. Stator is same, copy paste. Every stator manufacturer is like, I got you, fam. Rotor has to be re-engineered. It's a completely different design. Basically, instead of stamping or injecting magnet into it, you have to spool it up. So it's expensive. So nobody has figured out how to deal with mass production. I have only seen 2 OEMs right now that have already cracked the technology. Let's see how many else can do. That is the best of everything. And another aspect is, because it's synchronous, and somehow it achieves power factor of 1, meaning your inverter is like, instead of having VA rating, it can actually utilize the kilowatt rating. So it's like, I'm awesome. But there is a tiny penalty that to inject current into the rotor, you do add a secondary circuit, but that's much lower. Like your main circuitry could be 100 amps, secondary circuit would be, let's say, 20 amps, something like that. But it does have a little bit of sister cost, but again, electronics are much cheaper than everything else, so people deal with it. So these are the options that you have. Now we come to the soul of motor. All motors have this soul. We call it windings, so to say. Basically, winding converts your electrical energy into magnetic flux. So sometimes stators always have it, but sometimes rotor also it is. Like I talked about my left motor, that puppy is awesome. So that motor also requires a winding in the stator like this, rotor. Now you can do that. Heck, most of your drill motor are generally that universal motor. I'm talking about AC line motors, so those are universal. So you have two technologies, three technology practically speaking in the market right now when you are designing your motor. First is round wire winding. Basically, whenever you see normal thing, that is that normal thing. You have round copper wire, you just go YOLO on it. So what's the benefit? Benefit is this puppy can handle high frequencies. So if you look into other motor manufacturer, they're like, hey, they're using hairpin. You look into Tesla, why they are using copper? It's like, yeah, it has higher skin effect tolerance, meaning this puppy can work at 500 hertz rather than 250 hertz of giant thick coppers. So you have to balance this out. If your design calls for super high frequency, you have to deal with round copper wire rather than square bars of hairpin, because again, at higher frequency, this becomes more effective. What's the penalty? Penalty is poor copper fill, meaning if you have 1 liter of space, how much copper is in there? You will be lucky to get 40 to 50%. So it's very inefficient. And again, if you want higher voltage, like insulation will become thicker, so your copper fill will go down. So that's the limitation. That's why even though we like it, we use it, we trusted on it for 1 century, and there is a upper limit of it. It's like, we can't really go too much about that. So that's the poor copper fill penalty. Then we come to hairpin winding. This is the new technology in the town. And again, it's not new technology, it's miniaturized, because we used to, literally all power plant generators are built with that. It's just that those puppies are so huge, they run water through it to cool it down. So hairpin winding is just very awesome, but it also allows you to compact the motor because it's much higher densely packed in terms of copper. So current, basically how much current you can move into this diameter goes up exponentially. So you can go from copper fill of let's say 40 to 50% to 60 to 80%. Some designs, most designs do not push that hard, but you can easily cross 60%. So it does have that benefit. So great copper fill. So if you need a lot of current, this is like, I got you, fam. That's my power plant. I got you, fam. But does come with a poor high frequency. So if you're like, what if I want ludicrously high RPM? Is like, no, I'm not made for that. So you have to design it. Like if you are like, hey, I want to use hairpin stator, you may have to increase your or decrease your pole count in order to get the same RPM. You have to balance it. And there is a third child in the play, that is PCB stator. Now PCB stators are completely unique, completely new, so to say. So this puppy does have certain benefits, and there is a penalty that we can possibility, where we can utilize this puppy in axial flux configuration, and we can directly have a rotor and motor and a stator, basically the whole package, that is so power dense that we can finally have direct drive motor in our wheel, basically in hub motor, where it's powerful enough, where you can have like let's say 50 horsepower in each motor itself, direct drive. This can deal with that, but again, the technology is a bit undercooked right now. So these are the three options. So these are that you have to deal with in terms of the soul of the basically rotating machine. Then we come to the future of this Omnisire product. So you started with the early days of 3-phase of delta connection. Some were weird motors where they had 3 Y output and 1 neutral internally wound. I have no idea why, but they did. So we started with 3-point coming out of the motors. Then we some companies have 4-point coming out, so you can do proper Y connection or utilize the rotor stator as an inductor if you wanted to do it for charging circuits. Now companies are moving towards 6 output like this puppy. It's from Kia. I have linked the teardown video down below. Now it's, if you're like used to 3-phase AC motor, it's like, don't all motors have that? Yes, but generally that is done for us, basically the consumer. So consumer can have delta Y, delta configuration or Y configuration, or even switch, basically start on Y, switch to delta for high oomph. So we can do that. Now can we do that here? No, it's not for that. You can do it, but it's not meant for that. What is meant for even greater. The greater technology is what we call open ending winding, meaning now you have 6 points of contact and you have 2 inverters. Basically you have 1 real inverter, 1 phantom inverter. It's like a power factor kind of deal. And you can control both sides of the coil. Now, is there a benefit to that? Yes. This outperforms everything. Flat out outperform. Dual inverter topology is like, bitch please to everything else. Flat out. It's like, bro, don't try. No, don't. So that's the awesome part. Penalty, you do have to have a manufacturer who can deal with these things, and you do need a complex inverter circuitry, but it is the most awesome side. So people will slowly move towards that because again, electrics are getting cheaper. Now we have another aspect, because again, you have to put something and forget about it. Skewing the rotor or stator makes sense. Now skewing basically helps you to reduce cogging torque, basically that jerk. And if you have a straight teeth, you can get locked scenario. You do not want that. And again, every time when you are hearing the motor, that simply means something is vibrating high frequency enough that your ears can pick it up. Wasted energy, not a good idea. So you want to skew that, basically take the rotor, it. Same thing as like squirrel cage. So people are, even with the magnet motor, they are like, okay, what if we have few stacks magnet like this, few stacks little bit left, few stacks even left. This is from Volkswagen. They have one of the best staggered. Tesla has like, one in the center going backwards, another going like this. So it has a V stagger. Most have like a linear stagger. This is the most smooth stagger. Now benefit, this means the bearings can last much longer. Meaning if you run this motor continuously without any issue, what is the addition of motor vibration to bearing degradation, this will have the least penalty. So people want to do that. Now my love motor, this puppy cannot support that because it's too complex, but you can rotate the stator, you can tilt or skew the stator, so you can get the same effect. And again, more than enough manufacturers, especially with the round wire designs, it's like that's not an issue. So that will help reducing the noise and making sure the lifespan is increased. AC brushless synchronous motor is the most optimum motor because it does not have any penalty of rare earth magnet and has one power factor and is synchronous motor and allows you direct control of the rotor current and rotor status. Super awesome system as long as you can crack the manufacturing. So it's almost like front loading the technology. Figure out the rotor manufacturing and then you'll be good. Now, how does these two companies are doing it, the two OEMs? One company is using PCB and that PCB is an induction coil that picks up energy from secondary coil. Now, this is the whole point. You send high frequency AC into the secondary coil. Secondary coil induces current into AC current into the pickup coil. Pickup coil sends it into DC bridge rectifier. Bridge rectifier sends DC current into the rotor. And this DC control you can control by this high frequency AC. Benefit of that, you can precisely control how much oomph the rotor has. And again, at high speed, you want that to be low. At idling mode, you want it to be off. Induction motor does have that benefit. Basically, if you have two induction motors, front wheel and rear wheel, both have induction motor, you can turn one of them off. You can't do that if you have magnets. Magnet will always create a drag, magnetic drag like of eddy currents, even if the motors are floating. So it will cause an issue. Here it's like, bro, turn it off. Turn it off means turn it off. It's off. It's done. You will only have bearing drag. So that's a good thing. And this company has figured out how to have that in hollow shaft itself. So in terms of packaging, this is better. I think it should be better in terms of cost. Although both of them feel stupid to me. It's like, this is awesome. Motor awesome. Engineering ultra awesome. Why the heck you have hairpin in the stator, not in the rotor? Rotor needs hairpin. Why? Hairpins are awesome at DC. What does have DC in here? Rotor. We have been making power plant generator for 1 century with hairpin. Why the heck you have coil wires in there? And again, if you need that skewing, which again, both of them are either don't have skewing or not showing the skewing, it's like use copper system, round wire coppers for stator, skew the copper, benefit, high frequency is now unlocked and you can have DC, ultra high DC current with low skin effect losses, high copper fill, so rotor can be lighter. Like it just feels weird, it just feels inverted. It's like you should have hairpin in the rotor, not in the stator. Stator loves AC, give it AC. Rotor loves DC, give it DC. So, and again, easy to produce in scale. That's right now what everybody's working on. How can we mass produce it? It's one thing to say, I can produce 10 of this 1 year. Again, that's how many of the electric aircraft motors are being built. But if you want like, Model Y and all that, and you could be scaling up for 50,000 motors per day. Yeah, every little step counts. Look into Monroe. They are doing awesome things in teardowns. So this is the future thing. And again, why the heck? It literally looks inverted. Literally looks inverted. Why it's inverted? This is the future. So this was my presentation on basically surface level of AC traction motors that we are dealing with. Hopefully you have liked it, learn from it. In that case, please click the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.